I welcome you all to Future Focus. In this class, we would be studying chapter Principle of Mathematical Induction of Mathematics of Class 11. So now we have understood what are the steps for solving mathematical induction problem. Also, we have given you some questions for practice. These questions, I hope you have all have attempted the questions given for practice. Now let us proceed to some more different problems. So we have done this problem as well of squares, adding the squares of numbers and product of two numbers we have also done. Then today we would be doing this problem. When the product is in the denominator, it is in fractional form, right? Now how to solve this problem? So for that purpose, first of all, the first step would be, let us take this statement as Pn, right? So this statement would be of the form Pn. So let us check if it is true for n is equal to 1. For P1, LHS would be it is your LHS and this is your RHS. So LHS would be 1 upon 1, 1 plus 1. That would be 1 upon 2, right? And this number 1 upon 1 plus 1. So it would also be 1 upon 2. Hence it shows that it is true for n is equal to 1. Now let us assume that it is true for n is equal to k. Second step. So your pk would be 1 upon 1 into 2 plus 1 upon 2 into 3 plus 1 upon 3 into 4 and so on till 1 upon k into k plus 1, right? So that would be equal to k upon k plus 1. Now let us check if it is true for n is equal to k plus 1. So for that purpose, your left hand side would be one upon 1 dot 2, 1 into 2 plus 1 upon 2 into 3 plus 1 upon 3 into 4 and so on till 1 upon k plus 1 into k plus 2, right? So the term before this term, this fraction would be, as you could see, we have product of two numbers, 1 into 2. Then the second number is repeated in the next fraction and 1 is added to it. Again, the third fraction would be second number is repeated and 1 is added, it becomes 4. So 1 into 2, 2 is repeated, 2 plus 1, it becomes 3. Again, 3 is repeated, 3 plus 1, it becomes 4. So the previous number before 3 would be 2. So the number before this fraction would be 1 upon, as you could see, the first number is repeated. So this number would be k plus 1. And you could see If second number is the first number of the second fraction, then the first number is 1 minus of the second number. So this number would be k, right? And you could see this is already pk, and you know that its value would be k upon k plus 1. So let us write its value. After replacing this whole problem value with k upon k plus 1, because already we know the value of this problem statement is k upon k plus 1. So we have replaced it with k upon k plus 1 plus the left fraction, which is 1 upon k plus 1 into k plus 2. Now let us solve it further. So let us take the LCM of this term. So it would become, denominator would become k plus 1 into k plus 2. Now in the numerator, you would get k, and here you have k plus 1. That means it would be multiplied by k plus 2 plus 1. So it would become k square plus 2k plus 1 divided by k plus 1 into k plus 2, right? So as you could see here, k square plus 2k plus 1, this is the identity you have already learned in the previous classes. As you know, let me explain this identity to you. It is a square plus 2ab plus b square. This is equal to a plus b whole square, right? So here you have k square plus 2k plus 1. That means your a, it is a square, k square plus 2 into a into b is 1 and b square. So it would become k plus 1 whole square, right? So here you would get k plus 1 whole square divided by k plus 1 into k plus 2, right? So k plus 1 will cancel out, and you are left with, what? You're left with k plus 1 divided by k plus 2. So this is your LHS. Now let us solve the RHS. So here in the RHS, you need to replace n with k plus 1. So n is equal to k plus 1. In the numerator, you would get k plus 1 upon divided by k plus 1 plus 1. So that would be k plus 1 divided by k plus 2, right? So LH is equal to RHS. That means it satisfies for n is equal to k plus 1. Hence, it is true for all values of n, right? Now, let us proceed to our next problem. So this is our problem statement, and let us assume that this to be Pn. So let us assume the statement to be Pn, right? Now you need to check for n is equal to 1. For n is equal to 1, you would get what? 1 divided by 1 into 1 plus 1 divided by 1 plus 2. So you would get 1 divided by 1 plus 1 into 2 into 2 plus 1 is 3. So you would get 1 into 2 into 3, that would be 6. Now in the RHS side, let us check for 1. So 1 plus 3 divided by 4, 1 plus 1 into 1 plus 2. So it would be 1 plus 2. So you would get in the numerator, you would get 4 divided by 4 into 1 plus 1 is 2 and 2 plus 1 is 3. So 4 would cancel out and you are left with 3 2s are 6. So LHS and RHS are equal. So it satisfies for n is equal to 1. Now let us assume that it is true for n is equal to k. So our pk would be 1 divided by 1 dot 2 dot 3 plus 1 divided by 2 dot 3 dot 4 plus 1 divided by 3 dot 4 dot 5. Here dot means multiply. So we are multiplying. First fraction pk would be, first fraction would be 1 dot 2 dot 3. That means 1 multiplied by 2 multiplied by 3. So here you could see the second number. The second number is 3, 2. So we are starting with 2. 2, 3, the next number. Then 3, second number is 3, 3, 4, then next number of 4, 5. So it would go till first number is k, second number is 1, k plus 1, third number is k plus 2. And you would get k into k plus 3 divided by 4, k plus 1 into k plus 2. Now let us check if it is true for n is equal to k plus 1. For n is equal to k plus 1, your LHS would be 1 divided by 1 into 2 into 3 plus 1 divided by 2 into 3 into 4 plus 1 divided by 3 into 4 into 5, right? And so on till it would go till 1 upon. You need to put n is equal to k plus 1. That means first term would be in the denominator would be k plus 1. And your second term would be k plus 1 plus 1. That would be k plus 2, right? And your third term would be k plus, third multiple would be k plus 3, right? So here, the term, the fraction before this fraction would be, as you could see, 2, 3, 4. That means the first number would become the second number in the previous fraction. That means your first number, k1, would become the second number in the previous fraction. And you need to write preceding number to the second number and succeeding number to the second number. That means 2 minus 1 is 1 and 2 plus 1 is 3. So your fraction previous to this fraction would be, this k plus 1 would become your second number, right? And the first number before this k plus 1 is k, and number after this k plus 1 would be k plus 2, right? So this would be your RHS. Here, as you could see that till from this term till this term, the problem statement value is this value. So you need to place this value instead of this statement. Now let us place the value. That would be k plus 3 divided by 4, k plus 1 into k plus 2 plus this term 1 divided by k plus 1 into k plus 2 into k plus 3. Now let us take the LCM of the denominator. So LCM of the denominator would be, so this would be your LCM for k plus 1 into k plus 2 into k plus 3. So in the numerator you would get k into k plus 3 square, right? Plus, as you could see, there is no k plus 3. So you would multiply the numerator with k plus 3. So you would get k into k plus 3 whole square plus 4. Now let us solve it further. So your next step would be k into k square plus 2ab. You need to open this identity a plus b whole square. So it would be k square plus 2ab. That would be 2 into k a into b. That would be 3. Plus 3 square is 9. And plus 4. This is your numerator. Now it would be divided by this whole 4 into k plus 1 into k plus 2 into k plus 3. So you would get k into k square plus 6k plus 9 plus 4 divided by this whole same numerator, that would be 4, same denominator, sorry, 4 into k plus 1 into k plus 2 into k plus 3. So in the numerator, let us take k inside. You would get k cube plus 6k square plus 9k plus 4 divided by same denominator. Now let us solve it further. 4k plus 1 into k plus 2 into k plus 3. Now let us try first factor. That would be k plus 1. So we need to form the factor of the numerator. If k plus 1 is the factor, so k plus 1 is 0 and k would be equal to minus 1. So let us try to put minus 1 in the numerator instead of k. So you would get minus 1. Cube of minus 1 is minus 1 plus 6. Square of minus 1 is 1 plus 9 into minus 1, that would be minus 9 plus 4. So here you would get minus 1 plus minus 9 is minus 10 plus 6 plus 4 is 10. So 10 minus 10 is 0. That means k plus 1 is a factor. Now let us divide the numerator with k plus 1 to get another factors, right? So to get k cube, k would be multiplied with k square. K square multiplied by 1, that would be k square. In the sign and cancel out, k cube would cancel out. And here you are left with 5k square plus 9k. Okay. So in the question, you would multiply with 5k. 5k multiplied by k is 5k square and 5k multiplied by 1 is 5k. So it would be 5k square plus 5k. Change the sign. 5k square would cancel out. You are left with 4k plus 4. So you would multiply with 4 plus 4. So 4 into k, 4k, and 4 into 1 is 4. So it would be 4k plus 4. Change the sign and cancel out. So this is your question. So this numerator would be further factorized into k plus 1 into k square plus 5k plus 4. Now let us write these factors. So your numerator would become k square plus 5k plus 4 into k plus 1. So we have two factors over in the numerator and we have three factors in the denominator. And here k plus 1 would cancel out. Now what you can do in the numerator is, by middle term splitting, you can factorize it further. So you would get, so on factorizing k square plus 5k plus 4. On multiplying, you would get 4. 4 into 1, 4. And on addition and subtraction, you must get 5. So its factors would be 4 and 1. So k square plus 4k plus k. 5 can be written as 4k plus k. 5k, right? Plus 4. Now from first two terms, you would get k as common and you're left with k plus 4. In the next two terms, 1 would get common and you are left with k plus 4. So k plus 4 in both, they would get k plus 4 common and you are left with k plus 1. So k square plus 5k plus 4 can be written as k plus 4 into k plus 1. So let us write it as, so here you are left with k plus 4 k plus 1 divided by 4 into k plus 2 into k plus 3, right? Now let us check the LHS side you have formed. This is your LHS side. Now let us check the RHS side. So your RHS would be k plus 1. Instead of n, you need to put k plus 1. So k plus 1 into k plus 1 plus 3 divided by 4 k plus 1 plus 1 into k plus 1 plus 2. So this would be k plus 1 into k plus 4 divided by 4 into k plus 2 into k plus 3. So as you could see, LHS equal to RHS. That means it satisfies for n is equal to k plus 1. So that means it is true for all values of n. Now let us proceed to our next question. So these are the questions for practice for you. So I would suggest you to practice all the questions. 4 questions are these and 8 questions are given, and they are of the same type as we have discussed, right? Now let us proceed to the next question. So using the principle of mathematical induction, prove that now it is of the product form. Till now we are doing the questions of the addition, right? So this question is of the product form. So your first step would be, let us take this statement as Pn, right? Now you need to check the LHS and RHS for n is equal to 1. So for n is equal to 1, 1 minus 1 upon 1 plus 1. So that would be 1 minus 1 upon 2. Take the 2 LCM. So 2 minus 1. So it would be 1 upon 2. In the RHS, you would get 1 upon 1 plus 1. So that would be 1 upon 2. So your LHS and RHS are equal. That means it satisfies for n is equal to 1. Now let us assume that it is true for n is equal to k. So pk would be 1 minus 1 upon 2 into 1 minus 1 upon 3 into 1 minus 1 upon 4 and so on till 1 minus 1 upon k plus 1 equal to 1 upon k plus 1, right? Now let us check for n is equal to k plus 1 if it is true or not. So your LHS would be for n is equal to k plus 1. So your LHS would be 1 minus 1 upon 2 into 1 minus 1 upon 3 into 1 minus 1 upon 4 and so on till 1 minus 1 upon k plus 2. As you could see in the each multiple, there is increase of 1. So in the first multiple, if it is 1 minus 1 upon 2, in the second multiple, the second fraction would be, the denominator number would be increase of 1. So the number previous to this k plus 2 would be k plus 1. So I would be writing another product. The product previous to this would be 1 minus 1 upon k plus 1, right? As you could see in the pk statement, the value of this product till this product is 1 upon k plus 1. So let us write this value as 1 upon k plus 1. Till this statement we have write 1 upon k plus 1. Into we have 1 minus 1 upon k plus, right? Let us solve it further. So you would get 1 upon k plus 1 as it is. Take the LCM, k plus 2. In the numerator, you would get k plus 1, k plus 2 minus 1. So that means 2 minus 1 is k plus 1. So you would get k plus 1 upon with k plus 1 into k plus 3. So your k plus 1 would cancel out and you are left with 1 upon k plus 3. Now let us solve the RHS side. So your RHS would be 1 upon, in place of n you need to put k plus 1. So it would be 1 upon k plus 1 plus 1. That would be 1 upon k plus 2. So as you could see, LHS equal to RHS. That means it is true for all values of n, right? Since it is true for n is equal to k plus 1 and n is equal to 1, right? Now our next question. Using the principle of mathematical induction, prove that a plus ar square plus ar cube and so on till ar n minus 1 is equal to a into r raised to power n minus 1 divided by r minus 1 for r greater than 1. Now let us solve it. So first step would be, we would be taking the statement as Pn, right? Let us check if it is true for n is equal to 1. So your LHS would be A r raised to power 1 minus 1. So that would be A r raised to power 0. So something raised to power 0 is always 1. So that would be A. Now in the RHS side, A r raised to power 1 minus 1 divided by r minus 1. So A r raised to power 1 is r minus 1 divided by r minus 1. So r minus 1 would cancel out and you are left with A. So A is equal to A, LHS is equal to RHS. That means it is true for n is equal to 1. Now let us assume it is true for n is equal to k. If it is true for n is equal to k, so your pk would be A plus AR plus AR square plus AR cube and so on till AR raised to the power K minus 1, right? You need to place K instead of N, right? So that is equal to A R raised to power K minus 1 divided by R minus 1. So you need to check if it is true. Third step, you remember? You need to check if it is true for n is equal to k plus 1. So for n is equal to k plus 1, your LHS would be A plus AR plus AR square plus AR cube and so on till AR raised to power k plus 1 minus 1. That would be AR raised to power k. Right? So as you could see, R is increasing in every term. So for first term is A, second term is AR. Third term is AR square. If it is R is for 1, this is R is for 2. Then R is for 3. So the term previous to this K, RK, you have RK minus 1. So that would be A, so it would be A, R raised to power K minus 1. Right? And you know from pk term the value of till this term, the value till this term is this value. So let us place this value instead of this. So it could be A R raised to power K minus 1 divided by R minus 1 plus A R K. Right? You are writing this term. So on taking the LCM, you would get A R K minus 1 plus this in bracket A R K into R minus 1 divided by whole divided by R minus 1. Let us solve it further. So your LHS would be A R raised to power K minus A. On opening this bracket, A is multiplied by RK minus A is multiplied by 1 plus ARK into R. So that means powers are same, sorry, bases are same, so powers are added. So that means A R raised to power K plus 1. Here you have K power and here 1. So K plus 1. Bases are same. R is same. So powers are added. Minus A R K divided by R minus 1. So ARK here minus A plus. So it will cancel out. Let us take R outside. Sorry, A outside. You would get A common. A is common. So you would get R raised to power k plus 1 minus 1 divided by r minus 1. So this is your right and left hand side. So let us solve the right hand side now. Now your RHS would be A, R. Instead of n, you need to put k plus 1. So r is to power k plus 1 minus 1. This whole in the bracket divided by r minus 1. So LHS and RHS are equal. That means it is true for n is equal to k plus 1. If it is true for n is equal to k plus 1 and n is equal to 1, where you already know that it is true for n is equal to k, that means it is true for all values of n, right? Now let us proceed further. So your next question is, let a and b be arbitrary real numbers. Using the principle of mathematical induction, prove that ab raised to power n is equal to a raised to power n, b raised to power n for all values of n belongs to n, right? So first step you remember is you need to let the statement as Pn, problem statement, right? So let us check LHS RHS for n is equal to 1. For n is equal to 1, this would be AB raised to power 1. So that would be AB only. Here it is A raised to power 1, B raised to power 1. So that would also be AB. So LHS and RHS are equal. That means it is true for n is equal to 1. Now let us assume that it is already true for n is equal to k. For n is equal to k, pk would be ab raised to power k, that is equal to ak to bk, right? Now let us take n is equal to k plus 1 and check for left hand side and right hand side. So your LHS would be ab raised to the power k plus 1. So this would be a raised to power k plus 1 into b raised to power k plus 1. Now let us take the right hand side. So it would be a raised to power k plus 1 into b raised to power k plus 1. So if it is true for n is equal to k plus 1, that means it is true for all values of n. So this is all till now, and we would be proceeding with this chapter of mathematical induction in our next video. Thank you.